Welcome to the electronics class for December the 14th. I have looked over the homework, which is in the form of a quiz. I see that one of you got a perfect score. Two of you got very close to a perfect score. The rest of you, not so much. So I am thinking today, I want to start off by going over the answers to last night's homework. Now, the downside is if I go over the answers to last night's homework, then that means that I can't allow you to just go in and retake the quiz, because I'm going to give you the answers right now. So, I'm kind of mixed emotions about whether I should go over the answers or not. But based on what I'm seeing there, I'm thinking, yeah, I really should. Hang on a sec. Brandon just got here. Let me let Brandon in. Okay, so yeah, I'm thinking it's probably worth our while to go over the homework problems, because although three of you seem to know what you're doing, the rest of you are having a little bit of trouble here. I mean, some of your scores aren't horrible, but some of them are. Okay, so let's look at the first one here. All right, so go into the assignment. And okay, so power and VERP tables, that was the one that was due today. All right. Come on, what's taking it so long here? Here we go. Okay, so we need to fill out this VERP table and then answer the questions. Okay, so the first question is, in which columns are all the numbers going to be the same? So you guys should realize that if we've got a series circuit, okay, by definition, the current in there, the current going through this guy is going to be the same as the current going through this guy, which is going to be the same as the current going through this guy, which is the same as the current that's going through the battery. So that's what it means to be a series circuit. So whatever numbers go into this square, the same number goes in here, same number goes in here, same number goes in here. All right, so that's the answer to the first question, is that the current table is going to be the same for all of them. Okay, and so then after that, now we need to start filling in some numbers. So tell you what, I think let's just go ahead and fill in the entire table here. That would be the best way to do this. So first thing that I'd recommend is let's figure out what is the total resistance. So if we've got 220 plus 350 plus 170, hopefully you realize that since they're in series, we can just add them all together, right? So 220 plus 350 plus 170. So when I add those all together, I get 740. And so that is the total resistance. And by the way, while I'm at it, let's just go ahead and write in the numbers here, because the resistor values, we don't even have to calculate anything. We just write those in. Okay, so now we know what the total resistance is. And the battery, the total current on the battery is going to be 12. All right, so knowing that, we can now figure out what the current is, because we can say that if we have a battery and only one resistor, if the value of that one resistor was 740 ohms and the value of that battery is 12, then we can use Ohm's law to figure out what the current is. All right, so it's just going to be V over R. V is 12. Our total there is 740. Okay, so the number that we get is 0.0162, which is 16 milliamps. Okay, or if you want, you can, sometimes it's better to put in the actual number rather than the modified number. So I'm going to put in 0.0162. If you instead put in 16.2 milliamps. I'll call that good. And in fact, even if you rounded it off and just called it 16 milliamps, I'm not going to worry too much about that. Okay, now because they're all in series, that means that every one of these is going to be the same. Okay. All right, so now we know the current going through each one of these. So look at this guy. If we know that the current that's going through him is 0.10162, and we know what his resistance is, then we know we can just take Ohm's law and rearrange it. So we can rearrange that to get R times I equals V. So if we just take this R, multiply it by this I, that'll give us this V. Okay, so I'm going to take that last number and I'm going to store that in my calculator. So I'm going to have to keep retyping it in. So 220 times that will give me 3.57. 350 times that is going to be 5.68. And then 170 times that is going to be 2.76. Now, if you didn't put that many significant figures in there, that's okay. I mean, if this one here, if you called it 3.6 rather than 3.57, that's good. And in fact, in your final answer, I did specifically tell you that you were only allowed 2 sig figs. So when you typed in the final answer, you need to take the 3.57 number and you need to round it down to 2 sig figs. But what I like to do is in the VERP table there, I like to carry an extra sig fig along, because that way you don't get what's called round off error. Because if you round off your numbers too soon, you can get yourself into trouble. So I wait until I get to the very end before I round off my numbers. And I recommend you do the same thing. Okay, so the last thing we need to do is we need to figure out what the power is. And so hopefully you guys remember the power is given by I times V. That's, by the way, that has a name. It's called Watt's law. When you take the test in, oops, there's no E on the end of that. When you take the test in January, if they ask you what is Watt's law, well, this is it. Just like this guy down here is Ohm's law, this guy up here is Watt's law. Okay, so if we just take I times V, so take these two numbers, multiply them together, and then that'll give you the number that goes in there. So I'm going to take 3.57 times our current, and I get 0.058. Now I'm going to take 5.68 times of the current, and I'm going to get 0.092. And then I'm going to take 2.76 times the current, and I'm going to get 0.045. Okay. And then if I want to get the total current or the total power, what I could do is I just add all of these guys and put it there, or I can take this voltage times that current and put it in there. Either way will give me the same answer. And it works out to be, let me erase this so I have some room there. So it works out to be 0.194. Okay. So whether I add these guys together in order to get it, or whether I multiply these guys, I'll get the same answer all the way around. Okay, so that is how VERP tables work. Okay, and so that is, now when I answer when I type my numbers in here, notice I specifically said I want 2 sig figs. So I have to round the number off appropriately for that. So be careful about that. Okay, so in the next one here, now we've got a circuit. This time they're hooked up in parallel. So the thing that makes a parallel circuit is that the voltage across this guy is going to be the same as the voltage across this guy, is going to be the same as the voltage across this guy, which is going to be the same as the voltage across the battery. So whatever number goes in the V column there, it will be the same for all of them. Okay, and what is the number that goes in there? Well, if the battery is 12, that means the number that goes here is 12. And since they're hooked up in parallel, that means every single one of these has 12 volts across them. And then for the resistors, again, I can just write, so 220 is R1, 350 is R2, 170 is R3. Now, in this case, our total is not going to be the sum of these guys because they're not hooked up in series. They're hooked up in parallel. So what I have to do is I have to use the rule that says 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. That's the rule that I have to use. Okay. So when I do that, let's see what I get. I get 1 divided by 220 plus 1 divided by 350 plus 1 divided by 170, okay? And the number that appears on my calculator right now is not our total. The number that appears on my calculator right now is 1 over our total. So I have to do 1 over that number. And so what I get is 75. And actually, I'm going to carry an extra sig fig along. I get 75.2. Okay, if I were to round it off to 2 sig figs, the answer would be 75. Okay, but I like to carry an extra sig fig along just to be safe. Okay, so that means that if I had one circuit with one resistor in it, if that was a 75.2 ohm resistor, and that was a 12 volt battery, this battery would feel the same resistance that the battery up here would feel. Okay, so I can use that to calculate the current then. So I know that I equals V over R. So the total current is going to be the total voltage divided by the total resistance. So 12 divided by my last answer there is 0.159. Okay. Now, how do I find out all of these other currents? Well, I use Ohm's law. I say that I equals V over R, where this V is the voltage across that resistor. This R is the value of just that resistor, and that'll tell me what number goes in here. And then I do the same thing for all of the rest of them. Okay. So 12 divided by 220 gives me 0.055. 12 divided by 350 gives me 0.034. And 12 divided by 120, well, I don't need a calculator for that. Okay, that gives me 0.1. Okay, and notice if I add all of the currents, that will give me the total current. Okay, I can't do that with resistors. I can't add the resistors in order to get this, but I can add the currents because that's the way that parallel circuits work. So I think this is a really, really good review of how series and parallel circuits work. And based on what I'm seeing on your quiz course, it looks like it's a review that is well needed. Okay, so now the last thing we need to do is just calculate the power. And to get the power, remember, power equals I times V. So I just need to take that I times that V, and that'll give me that power. And then I do the same thing for all of them. So 12 times 0.055 gives me 0.66. 12 times 0.034. Oops, hang on a sec. Okay, so 12 times 0.034. Okay, that gives me 0.408. 12 times 0.1 gives me 1.2. And then if I want to know what the total power is, In this case, I can add them up, or again, I could take this number times that number. Either way, it will give me the same answer. Okay, and so I get 1.91, and the answer there is going to be watts. Okay, so total power is 1.9 watts. Okay, which is a lot of power, actually. Those guys are going to get really warm. The power basically tells you how much they're going to heat up. Okay, and now the last one I suspect is the one that probably gave most of you the most trouble. Those of you that got like 10 on the quiz, I'm willing to bet that you got the first two circuits right. The thing that you had trouble with was this circuit right here. And this is one that I guarantee you'll have a problem like this on the test. When I say the test, I mean the one in January, the state mandated test. So tell you what, let me have somebody here answer this one here. Let's see, who do I want to answer this one here? All right, Caden, I'd like you to answer this one. And tell me, how did you approach this?
So like there's this one resistor, the 220 ohm resistor at the top, that and then it comes to a junction with two resistors after it.
Yes.
And you can treat that as the two resistors are are running in parallel, and then at the bottom, and then R1 is running in series with those two resistors.
Okay, so what I think I hear you saying is that you're recommending that we take these two that are in parallel and let's replace them with an imaginary circuit that has a 220 ohm resistor up here, but this resistor here is whatever we get if we replace these guys. Is that what you're telling me?
Yeah, and then
Okay.
once you have the two resistor values, you can then combine it into one resistor to find the total resistance that the battery feels.
Okay, so I'm going to use this equation to figure out what the value of this resistor is. Okay, so I'm going to take 1 divided by 350 plus 1 divided by 170. And so the number that appears on my calculator is not our total. The number that appears on my calculator is 1 over our total. Okay, so I have to take 1 over that. So I get 114. All right, so Caden is suggesting that the next thing we do is we replace this with just one resistor where these two guys together have been combined to get him. And since those are hooked up in parallel, or I'm sorry, in series, we can just add them. Okay, and so what we're going to get then is that this guy has a total resistance of 334. Okay, so we can now put that in here. So their total resistance now is 334. And R1 is, of course, 220. R2 is 350. And R3 is 170. But notice our total is not just the sum of these guys. We had to get our total by combining those two parallel resistors together. And then once we got that, then combine the two two series ones together. Okay. All right. So Caden, what do you recommend we do next?
Well, you could use the resistor values to find the voltage across each resistor and then find the total.
Well, what I would recommend is first thing let's do is let's find out the current through this guy right here. That's what I would do. So if we know the total voltage is 12 and we know the total resistance is 334, so I would use that to find out the total current. So 12 divided by 334, okay? And so 12 divided by my last answer there. So I get that the total current is 0.0359. Okay, So that's the current that's flowing through this imaginary circuit. That's the current that the battery is putting out. And that, okay, so we know that the current that's flowing through this branch right here, up until we get to the junction, that current is 35.9 milliamps. Notice that that's the current the battery is putting out, but that's also the current that's flowing through R1 because R1 is in the same branch as the battery. Okay, so now we know what the current is through R1. It's going to be the same as the current through the battery. So 0.0359. So now that we know the current flowing through R1 and we know how many ohms R1 is, we can use that to figure out what is the voltage drop across R1. Okay, so you see how VERP tables are actually kind of helpful. We can really understand things a lot better. So we know V equals R times I. All right, so if R is 220 and I is 0.0359, so that tells me that the voltage across R1 is 7.89 volts. Okay, so the voltage across this guy, delta V, is 7.89. So if we started off with 12 volts here, 12 volts here, 12 volts here, 12 volts here, when we cross over to here, we're going to lose 7.89 volts. So if I just take 12 minus 7.89, that will tell me what is the voltage, the absolute voltage right there. Okay. So I get 4.11. So that means that if I've got 0 volts here, 0 here, 0 here, 0 here, the absolute voltage here is going to be 4.1. When I say absolute value, I mean how many volts is it higher than ground? And so now I know what the voltage is across these guys. So the voltage across both R2 and R3 is 4.1. Okay, actually 4.11 if I carried my extra sig figs out. Okay, so now that I know the voltage and I know the resistance, I can figure out what the current is because again, current equals voltage over resistance. So if I do 4.11 divided by 350, so that tells me that the current here is going to be 0.012. And if I do 4.11 divided by 170, that tells me the current here is 0.024. And now that I know the voltage across each resistor and the current through each resistor, I can then figure out how much power each resistor is using. So 7.89 times 0.0359. And so that gives me 0.283 watts. So 283 milliwatts. And now for the next one, I do 4.11 times the current, which is 0.012, and I get 0.049, or 49 milliwatts. Now I do 4.11 times 0.024, and I get 0.099 or 99 milliwatts. And then if I want to know the total current or the total power, I can just add up all of the power separately, or I can do that voltage times that current. Either way will give me the same answer. And that answer works out to be 0.431 or 431 milliwatts. Okay. This is something that you guys need to know how to do. And when I look at the scores here, what I'm finding is that some of you know how to do it quite well. Others of you can kind of sort of do the simple ones, but the hard one you have trouble with. And a few of you weren't able to do, you either weren't able to or just chose not to. Some of the scores that I see here are low scores. So I see that you tried it, just didn't do it very well. A few of you didn't even try it. Guys, you really have to do this. I guarantee there will be a question like this on the final exam. And I want everybody to get this right. So what I've done is in tonight's homework, I've given you another one of these VERP problems. And I gave you one that was similar to the very last one, because the last one is the tricky one. I mean, if you can do the last one, then for sure you can do the easier ones. So expect another problem like this in your homework tonight, where you have to do another VERP table for a circuit that is combined series and parallel together. And this time I want to see everybody get it right, okay? All right. Now, in addition to this, I want to also do the quick quiz like we've been doing for the last couple times. So everybody get ready. I'm going to want you to type something into the chat box, but I'm going to want you to type it in a private message, not a public message. So there we go. I want you guys to tell me in a private message, what does that schematic symbol represent? What electronic device is that? Okay. All right. A few of you are admitting that you don't know, and I appreciate your honesty. And there's no judgment right now. But by January, I want you to know. Okay, and the rest of you, it looks like about half of you have identified that this is a transistor. And in fact, you even took it one step further. You recognized that it's in the family of transistors that we call Mosfets. So everybody take careful notes here. I see a few of you are telling me in the notes here, you're saying, well, you haven't studied this yet. Well, we have talked about it. I mean, you personally might not have studied it, but the rest of us have talked about it, and we've talked about it several times. So I want everybody to get this. Okay, so if we take, let's just do a family tree. So if we start with all transistors of all types, they can be broken up into two general subgroups. One is called BJT, which stands for Bipolar Junction Transistor. And the other is Mosfets, which stands for Metal Oxide Semiconductor Field Effect Transistor. Now, the important thing about BJTs is that they are current-based, okay? What that means is, in order to turn on a bipolar junction transistor, current has to flow into the transistor through the input terminal. So transistors have three terminals. Okay, this one here is let me call it the signal input, or let me call it the control input. Okay, this one here is the main current input. And this one here is the main current output. So basically what's going to happen with a transistor is we have a big battery over here, and we want a lot of current. We want a big current to flow through this transistor, okay? But we want to control it using a small input, okay? So if the transistor is a BJT transistor, we have to actually send current into the transistor in order to turn it on. If, on the other hand, it's in the different family of transistors, the family that's called MOSFETs, okay, those are not current-based. Those are voltage-based. And what I mean by that is that if the transistor that we have is a MOSFET, the way that we turn the MOSFET on is by putting a positive voltage on the input terminal for our control input, but current does not actually flow. This transistor that we're looking at right now, this transistor is in fact a MOSFET. So that means that when we put voltage on here, current does not actually flow. And you can see by looking at the thing here, the reason why it doesn't flow, because we have a break. The left side of this thing and the right side of this thing are not connected together. So we put voltage on there, but electricity does not actually flow into the input gate, okay? That's what makes a MOSFET different from a BJT. With the BJT, current has to flow into the control input. But with a MOSFET, you put voltage on there, but once that voltage is established, no current actually flows. Okay, so this is a transistor, and it's a member of the MOSFET family of transistors. Now, the next thing you need to identify is whether it's an NMOS or whether it's a PMOS. And the best way to understand that is let's look at this diagram right here. Okay, so you can see that what I've done is I have broken the transistors up into two different types. On the right side, I have the bipolar junction transistors, what are also called BJTs. And on the left side, I have the MOSFETs that are called metal oxide field effect transistors. Okay, right? And so in all cases, the gate, the input that you see in the middle here, this is always the control input. This is always the thing that we manipulate in order to turn the transistor on or turn the transistor off. So if the transistor is turned on, then current will flow, and current always flows into the top and out of the bottom. And it doesn't matter whether it's a bipolar junction or a MOSFET, they always follow the same pattern. This terminal right here is the one that turns it on or off. This terminal up here is the one that's connected to the plus voltage. And this terminal down here is the one that's connected to the ground, or you could say, or the minus voltage. Okay. All transistors work that same way. Okay. Now, let's look at bipolar junction transistors. So with the bipolar junction transistor, hopefully you guys remember that this is made of two diodes that are connected back to back. Okay. And this represents one of the diodes. Now, if it's back to back, that means the other diode is like this, because the tail of this guy and the tail of this guy, they go together. Okay, now if they're hooked up like you see on the right here, then the other diode is like this, because we need the heads of the diodes here are the same, whereas over here it's the tails of the diodes that are the same. And whenever you have a diode, okay, it always goes from P to N, because electricity always flows from the positive side to the negative side. Okay, so if this is the arrow and it always goes from P to N, then that means that if we focus our attention, if we focus our attention on this guy right here, that means that this is our PN diode. And so that means our other diode here is PN. So then if we name them starting at the top and going to the bottom, so we got N, P, N. Whereas this guy here, this is our P, oops, sorry, let me fix that. So this is our PN diode, and this is also a PN diode. So you can see if we start at the top, which is where we always start, PNP. So this is a PNP diode. Okay, so you guys should be able to recognize this symbol, recognize, and you see how where we have the control input, you see how that line is actually connected to this line there, whereas over here they're not connected, but over here they are connected. So that means the current will actually flow. So when you send current, it actually, electricity flows into here and it comes out here, as opposed to a MOSFET where it doesn't actually flow. You just have to put the voltage there, but once the voltage is established, current doesn't flow, right? So I guarantee they'll have questions like this, where they'll give you a symbol like this and they'll say, what is it? And you need to recognize that's an NPN, bipolar junction transistor. And they'll say, what's this? And you'll need to recognize that's a bipolar junction transistor, PNP. Now, what do you do for MOSFETs? Okay, well, notice the arrow here works the same way as the arrow here. If this was a bipolar junction transistor, this would be the P, this would be the N, and which means this one up here would be an N. So notice if it was a bipolar junction transistor, it'd be an NPN. Notice it starts with the letter N, so it also starts with letter N up here. Whereas in this case, if this was on the right here, this would be a PNP if it was a bipolar. And so the first one there is P, the first one here is P. So that's how you know. Now, sometimes they don't put the arrows. And so then you got to kind of think, okay? So if you see the little dot right here, okay, what that means is that that's like an inverter. And so the thing about if you have an NPN transistor or an NMOS transistor, what that means is in order to turn the transistor on, you need to put plus voltage on the control input. Okay, so for an NPN or an NMOS, the way you turn the transistor on is by putting a plus voltage on the input gate. That will turn it on. With a PNP, what you need to do is you need to put a minus voltage on the input gate. And the same thing applies with a PMOS transistor. What you need to do is you need to put a minus voltage on the input gate. And this inverter there turns it to a plus. So by putting a minus voltage right here, this inverter makes it be plus, which then makes it turn on. And so this way you know that it's a PMOS. Okay. So there's lots of ways that they could ask this question on the test in January. What they could say is something like this. They could say, I've got a transistor and I want to turn it on. And I find that in order to turn it on, I need to apply a negative voltage. A negative voltage is what turns it on. And then they're going to say, what kind of voltage, what kind of transistor is it? Well, you know that whatever kind of transistor it is, it starts with the letter P. And if, on the other hand, if it takes a positive voltage in order to turn it on, okay, then a positive voltage means that it's a transistor that starts with the letter N. Okay. So be aware of that. Now, there is one other thing we need to talk about with transistors. You know these three terminals that we were talking about? We've got this terminal here, which is, the same. So these terminals that I've marked in red here, those are what I call the control inputs. That's the thing that causes the transistor to either turn on or turn off. Okay. And now in blue, I'm going to mark these guys. So the blue terminal, that is the one that you always need to connect to the plus voltage. And then I'm going to go to green here. So the green terminal, okay, that's the one that you need to connect to the negative voltage. Okay, so when you apply the appropriate signal on the input, that will either turn or if you put the right input in there, that will turn the transistor on. So then the voltage can flow from the plus to the minus, and it always flows like that. Now, the thing that's a little bit annoying is that for whatever reason, the people who made the transistors, they gave them slightly different names for these three inputs, depending on whether they're a MOSFET or a BJT. Okay, so if I drag these over here, okay, if it's a MOSFET, the control input is called a gate, and the input that gets connected to the plus voltage is called a drain, and the input that gets connected to the minus voltage is called a source. Please write this down in your notebooks. And it doesn't matter whether it's a PMOS transistor or whether it's an NMOS transistor, it works the same way. The control input is called the gate. The input that connects up to the plus voltage is called a drain, and the input that connects up to the negative voltage is called the source. Okay, so this here is always the plus V, this guy here is always the minus V, and this guy here is always the control. Now, if it is a bipolar junction transistor, then for whatever reason, they decided to call it something different. Instead of calling it a gate, they call it a base. Instead of calling it a drain, they call it a collector. Instead of calling it a source, they call it an emitter. Now, it doesn't matter if it's an NPN or a PNP, okay? It always works the same way, okay? Whatever you've got as your control input, if it's a BJT, that control input is always called a base. If it's a BJT, the thing that you connect to the plus voltage is always called a collector, and the thing that you connect up to the minus voltage is always called an emitter. If it's a MOSFET, then instead of calling it a drain, they call it, or instead of calling it a collector, they call it a drain. Instead of calling it a base, they call it a gate. Instead of calling it an emitter, they call it a source. That's just the way they chose to do it. And I understand it's kind of confusing, but that's the way they did it. So please memorize that. Okay. So I'm going to pause here for just a second while you guys write this down. Okay. I want you to make note of the fact that if it's an MOSFET, the three terminals are called the gate, the drain, and the source. If it's a BJT, the three terminals are called the base, the collector, and the emitter. Okay. All right. So next time we meet, I'm going to give you another little quiz about this, and I want you guys to be able to get it. So, like, one thing that I might say next time is I might say, I've got a transistor, and one of the terminals on this transistor is called the emitter. What kind of transistor is it? Is it a MOSFET or is it a BJT? Well, you should know that if one of the terminals is called an emitter, it's a BJT, not a MOSFET. That's the kind of stuff that I want you to know. So I trust you guys are taking notes here. Okay, let's go back to our regular quiz here. So again, I want you to get ready to type into the chat box. Tell me, what is this, guys? Type it in a private message. Tell me what device is this? Okay, good. I'm seeing lots of answers coming in, but I need to see more. Okay, it looks like everybody has pretty well got it. And those of you that answered, you all answered correctly. It is, in fact, a capacitor. And you should recognize that there are different types of capacitors. If you see a plus sign written on the capacitor, that means that it's what we call a polarized capacitor. Polarized. Boy, for some reason it doesn't want to write. There we go. Okay. Now, this is what I'm just going to call a normal capacitor. I probably shouldn't call it normal, because actually polarized capacitors are pretty common. Let me just call this a non-polarized capacitor. Okay. So a non-polarized capacitor, you don't need to worry about hooking it up backwards. It'll work fine no matter which side you connect to the plus and which side you connect to the minus, it'll work fine. But if it's a polarized capacitor, you got to be careful. And it'll tell you on the capacitor which side is the plus side. And so make sure that you connect that to the plus side of the battery and the other one to the negative side of the battery, because if you hook it up wrong, it will not work the way it's supposed to work. And then this one here, you know that because of the arrow, that's our way of saying that it's a variable capacitor. That means it's a capacitor that has a little knob on it. And by turning the knob, you can change how much capacitance it has. All right, what is this? I need you to type in the chat box, what is this? Okay. All right, a fair number of you are saying you don't know. And we did talk about this briefly, but it was brief. So it looks like the majority of you have recognized that it is a switch of some type. Okay. So this is what we call a momentary switch. Imagine that there is a little spring right here, and it's inside a box. Okay. And this is the button that's sticking out. So when you push on this button, this guy is going to lower down and come in contact with these two terminals. And when that happens, then electricity can flow through the circuit. As soon as you take your finger off the button, then it's going to spring back to this position here. And once it springs back, then the current cannot flow anymore. So this is a switch that is only on as long as your finger is pushing on the button. As soon as you release your finger, then the electricity stops flowing. All right, so this is something that we call a momentary switch. Okay. Now, one of you took it even one step further. One of you said that this is a momentary switch that is normally off. And when we say normal, what we mean is when your finger is not pushing the button, is the switch turned on or is the switch turned off? So in this case, if you have a picture that looks like this, that means that this is a switch that is designed in such a way that if you are not pushing the button, the electricity cannot flow. So this is a normally off momentary switch. Now, there are other kinds of momentary switches. Okay, so what you see on the right side now, this is a normally on momentary switch. Okay, so again, imagine that there's a little spring right here. So if I'm not pushing the button, the spring is pushing it up here. And so you can see that the left side and the right side are connected so electricity can flow. So when I push on this, I'm going to compress the spring. And so this thing is going to lower down here. So when I push on it, what that's going to do is that's going to stop the electricity. Whereas over here on the left side, when I push on it, that starts the electricity. But on the right side, when I push on it, that stops the electricity. So the one on the right is what we call a normally off momentary switch. And the one on the left is what we call a normally off momentary switch. And on the one on the right is what we call a normally on momentary switch. Okay. Now, what if we have a kind of a switch that isn't spring-loaded like that, so that when we flip the switch, even if we take our finger off, it stays flipped? Okay, so this is the simplest kind of switch there is. It's currently in the off position. If we push it down, then it goes like that. So then it's on the on position. And if we take our finger off, it stays in the on position. So this is not a momentary switch. This is what we call a toggle switch. So when we do whatever we do to the switch, when we take our finger away, it doesn't spring back like these guys do. It stays in whatever position we put it in. So that's called a toggle switch. Okay. So all of these are different types of toggle switches. And by the way, this is the new thing that is your main homework tonight. Today, the main subject for today is switches and relays. Relays are just a different kind of switch, really. Okay. So what does this SPST mean? Well, that means single pole, single, and then let me make a little room there so I can write the last word, throw. Okay. SPST means single pole, single throw. So what does pole mean? Pole means how many input terminals are there. So if we got SP, that means we got a single pole. We've only got one input. This is also SP. Notice we got one input. This one here is DP. The D stands for, oops, the D there stands for double. Okay, so that means I've got two inputs. Okay, and over here I've got a DP, which also means I've got two inputs. Okay, and over here I've got 4P. That means I've got four different inputs. Okay, now what does the T stand for? The T is throw. That means for any given input, how many possible outputs are there? So if let me clean up here. My picture is getting pretty cluttered. So if we look at this, here I've got one input, and notice I've only got one output. Okay, so if I flip the switch to the open position, current does not flow. If I flip the switch to the on position, current can flow. I've got one input, one output. So all I can do is I can break the current, but that's all I can do. But in this case where I've got over here, I've got double throw. That means I've got two possible outputs. So the switch can be one of two ways. If the switch is as shown here, then what that means is the current comes in and it goes out the upper switch. Now, if I were to flip the switch the other way, then what would happen is the current would come, let me do that in a different color here. So if I flip it the other way, the current comes here and goes out. Okay. So instead of being off on, what I can do is I have a fork in the road, and I can direct the current either on the left fork or the right fork. Now, I could use a single pole double throw switch the same way that I use a single pole single throw switch. If all I really want to do is just let the current flow or not current mod, what I could do is I could take my battery and I could hook it up like this. And then down here, I could do the same thing. I could take the battery and I hook it up like this. Okay. So in this case, the switch on the left and the switch on the right are both going to behave the same way. When I put the switch in the configuration shown in the drawing, electricity does not flow. And then if I put the switch in the other mode, then electricity does flow. The thing that's different about the double throw switch is it gives me a little bit of freedom that if I wanted to, what I could do is I could have it so that instead of just being a simple off on, what I could do is I could direct the current in a different way. I could maybe have a more complicated switch so that the current goes this way instead of just breaking it. I could have it, there's two different paths, and I could have it take one of the two different paths. Okay. All right, so now let's look at this next one here. I've got double pole, single throw. Okay. that if I break that up, so the DP part of that double pole means I have two inputs. But for any given input, you'll see there's only one output. Okay, don't look at the total number of outputs. Just look at how many outputs are there for any one input. So in this case, you can see that this one input right here, he can either get through or he doesn't. There's no, he can't take two different paths. He can only take one path. This guy here, same way. He can either go through or not. He doesn't get two different paths. So we say that this is a single throw. It may have two inputs, but each input only has one possible output. So we're going to call that a single throw. That's a double pole single throw. And over here, you can see there's a double pole double throw. And over here, you can see this is a 4 input. So that means it's 4 poles, but each input only has 2 possible outputs. So that means it's a double throw. Is this making sense? Now, the last one is the one down here, which is kind of interesting, I think. In this case, you can see we've only got one input, so that means it's a single pole. But you can see there are 4 possible outputs. So basically what we've got here is a switch that we can rotate. It's got a little knob on it, and we can rotate the knob. So we can take that input and we can direct it to one of 4 possible outputs. So that means this is a single pole with 4 throws. Okay, does that make sense? So I'd like you guys to type in the chat box, say yes, this makes sense, or no, you've got questions about it. So I need to see everybody type in either yes or no. Okay, good, I'm seeing some messages there. Okay, looks like everybody's saying this makes sense. Okay, good, yeah, switches are pretty simple. So when you guys take the test in January, you're going to have to identify, so it's kind of like with transistors, you know, you got 2 families of transistors, you got BJTs and you got Mosfets. So with switches, the first thing you got to ask yourself is it a toggle switch or is it a momentary switch? Okay, that's the first thing you got to ask yourself. And then the next thing you got to ask yourself is it a SPST or SPDT, or is it a DPST or a DPDT, or is it something else? And we have a generic way of writing this something else. We call it XPYT, where X can be any number. In this case, X is 4. Y can be any number. In this case, Y is 2. So we could call this a 4P2T. So 4P2T, that's what we call it, but XPYT is just kind of a generic way of representing all of them. So this one right here is also an XPYT, where X is 1 and Y is 4. Okay, so I think that's pretty straightforward. Okay, so that's switches. Now, what about relays? What is a relay? Well, a relay is very much like a transistor. A relay is something where you've got 3 different, well, I better not say 3, but you've got a control. So let me, let's see. Hang on a second. So let's look at this thing right here. So, and in fact, let me even, let me zoom in on it here. Okay. Okay. All right. This is very much like a transistor. This thing that you see on the left side here, okay, this is the control. This is something where we can send in a signal and it will turn on this inductor, which by the way is an electromagnet. So So this inductor that you see here is an electromagnet. So when we send current through here, it creates a magnetic field. And this switch here is a magnetically controlled switch, a magnetic switch. So, and it's got a spring on it. So if we have electricity flowing, then it goes one direction. If we don't have electricity flowing, then it goes the other direction. Okay. So what we can do is we can use the control to turn on and turn off a much larger current. So this control could come from something really weak, like for instance an Arduino. You guys know that Arduinos are wonderful inventions, but they can't put out very much voltage and they can't put out very much current. They can only put out a maximum of 5 volts, and they can only put out a maximum of about 20 milliamps. Now, it turns out that 5 volts and 20 milliamps is enough to turn on this magnet. And once you turn on this magnet, that flips the switch here. And so that makes it so that the electricity can flow through this. And so like we could have, 100 volts, and we could have, like maybe 50 amps or more. That we control this high voltage, high current by using an Arduino, which has low voltage and low current. So a relay is just an electrically operated switch. That's all a relay is. And so on all these relays that you see shown here, on the left side here, you've always got an electromagnet. And this thing over here may not look like an electromagnet. It's just a lazy man's way of drawing a relay. So this thing is also an electromagnet, even though you don't see the coils. Okay. So a relay is when you take an electromagnet and you hook it up in such a way that when you magnetize it, the switch either closes or opens, or it switches onto different paths. So relays come in SPST versions and SPDTs and DPSTs, all those different single pole, single throw things that we talked about with the regular switch. Well, those apply with relays as well. Okay, so let's start with this guy right here. So when we see this, we know it's a relay. So what we do is we look to see how many inputs do we have? And I see, well, it's only one. So that means it's a single pole. And then I look to see how many outputs do I have? And so you see I only have one output, so that means it's ST. So this is an SPST relay. This guy over here is an SPDPT relay, okay? Because it's got one input, but that one input could either flow this way or it could flow that way. It's got 2 different directions it can go. That means it's a double pole. So single pole double throw relay. This guy on the bottom, you see we've got 2 inputs, but each input only has one possible output. So that means that this guy on the bottom left here, he is a double pole single throw relay. Whereas this guy right here is a double pole double throw relay. Okay. This guy over here is also a double pole double throw relay. This guy right here, this is the input. So this is a single pole. And you can see that input can get directed this way or it can get directed that way. So you see we have 2 possible ways it can go. So that means this is a single pole double throw relay. This guy up here is also a single pole double throw relay. Okay. All right. Does that make sense? You guys good on that? Okay. So your homework tonight, well, first off, you're going to have a bunch of questions about switches. And so you're going to have to identify, is it a momentary switch? Is it a toggle switch? Is it a SPST switch, or is it a DP-DT switch, or is it an SPDP switch, or is it a XPYT switch? Okay, so you're going to have to identify those. And then the last thing in your homework is going to be a circuit that's going to look very much like this. The numbers will be different, but the arrangement will be very similar. And what you're going to have to do is you're going to have to fill out a VERP table. And this time, what I'm going to want you to do is after you fill out the VERP table, I'm going to want you to take a photograph of the VERP table and upload the photograph to me so that I can see that you've correctly filled in all of the openings in the VERP table. All right, that's it for today. Are there any questions before we end the class? Okay, not seeing any, not hearing any. So if you guys want to type bye into the chat box and head out, I'm okay with that. And if you had a question but you didn't want to ask because you knew it was being recorded, here what I'll do is I'll stop the recording so then you can ask your question without embarrassment.